Hey everyone. Let's see. So we've learned a bunch of tests so far. We had the alternating series test last time. Today we're going to learn two more tests, and that'll be the last of the tests that we'll need for this quarter. Before we get to the test, though, we're going to introduce a new concept, and it goes like this. So a series sum n equals k to infinity a sub n is absolutely convergent if sum n equals k to infinity, absolute value of a sub n is convergent. So what's happening here? The original series is called absolutely convergent if when you put absolute value bars around it, you get a convergent series. So for example, sum n equals 0 to infinity of minus 2/3 to the n is, and I usually abbreviate absolute convergence with an AC, right? So this series is absolutely convergent, and the reason, the reason, so what am I supposed to do? I want to take my series, put absolute value bars in. So if I look at the sum n equals 0 to infinity of absolute value, negative 2/3 raised to the n, that's going to give me the series. I'm just going to get rid of that minus sign right there. So that'll give me a 2/3 to the n, which we know converges by, well, this is a convergent geometric series, so it converges by the geometric series test because we know that that number right there, 2/3, has absolute value less than 1. So because the series that we get when we put absolute value bars around it converges, we conclude that the original series is absolutely convergent. Here's another example. So let's look at the sum n equals 1 to infinity minus 1 to the n plus 1 times 1 over n. Now, we showed last time this series right here is convergent. So this is convergent. This is a convergent alternating series, so this is convergent by the alternating series test, but it is not absolutely convergent. And the reason, so let's see what happens when we put absolute value bars in. So sum n equals 1 to infinity, absolute value minus 1 to the n plus 1, 1 over n. When we put the absolute value bars in, what do we get? Right, this is sum n equals 1 to infinity, 1 over n. That's the harmonic series, right? That one's a divergent p series, so this one diverges. P equals 1. Right, so we've got an example of an absolutely convergent series and something that is not absolutely convergent. And that leads to, so this last example leads to another definition. So the series sum n equals k to infinity, a sub n is conditionally convergent if it's convergent, so if it is convergent but not absolutely convergent. So this last example that I did, I'll write this down. This last example, this is an example of a conditionally convergent series. It's convergent, but it's not absolutely convergent. So, all right, let's do this example. by the work that we did just a second ago, the alternating harmonic series is, I abbreviate it CC, conditionally convergent. It's convergent, but not absolutely convergent. So now, oh, yeah, I need to say this first. So here's a fact. If it's absolutely convergent, then it's definitely convergent. So if the series is absolutely convergent, then the series is convergent. Now, what that means is there's now three options. Anytime you have a series, one of three things is true. Either the series is absolutely convergent, conditionally convergent, or divergent, right? So those are your three options. And so now, oftentimes, the instructions for the homework problems or whatever kind of problems you get are going to ask you to determine whether a series is absolutely convergent, conditionally convergent, or divergent. Okay, so now let's look at some examples, and the instructions are going to be the same for all of these. So what we want to know is it absolutely convergent, is it conditionally convergent, or is it divergent, right? So now we know any series, for any series, one of those three things is true. All right, so as a first example, let's look at the sum, n equals 0 to infinity, minus 1 to the n times n over n squared plus 1. So first, if we compute the limit as n goes to infinity of n over n squared plus 1, that limit's equal to 0. So what did I just do? I applied, we've got an alternating series here, I applied the alternating series test, and so this series converges. So, and I need to be careful here. So sum n equals 0 to infinity, minus 1 to the n over n plus 1, n squared plus 1, converges by alternating series test. Okay, so we know that it's at least conditionally convergent, and now we need to check to see whether it's absolutely convergent. So now consider the series that you'd get if you put absolute value bars around it. So this will be sum n equals 0 to infinity, n over n squared plus 1. Right? If you put absolute value bars around it, all it's going to do is kill off that minus 1 to the n right there. Okay, so this series right here, when you look at this one, you should have a suspicion. This one is going to behave like a 1 over n, right? The dominating term here is an n squared in the denominator. So this one's going to diverge, right? So how do you use that? Limit comparison test would be the right test to use. So since limit as n goes to infinity, n over n squared plus 1 divided by 1 over n, you can check that limit's equal to 1. And sum n equals 1 to infinity of 1 over n diverges, p equals 1. So does the one we started with, n equals 0 to infinity, n over n squared plus 1, by the limit comparison test, right? We limit compared it to one that we know diverges. That means that ours diverges. And you know, I noticed as I started going, it's kind of silly to put a lower limit of n equals 0, right? Because that's going to give us a 0, 0, 0, 0. So I really should have, it doesn't matter, but I should have done this example with n equals 1 as the bottom. Okay, so what's our conclusion? The original series converges. The series that we get when we put absolute value bars around it diverges. So our conclusion, conditionally convergent. So conclusion, sum n equals 0 to infinity minus 1 to the n over n squared plus 1 is conditionally convergent. And same instructions. Let's do another example. So let's look at the sum. N equals 1 to infinity. This is going to be sine of n divided by n cubed. Now, if you notice, I did 2 steps in that last problem, and that's because I knew it was going to be conditionally convergent. When I saw that, I saw the n in the top, the n squared plus 1 in the bottom. That tells me it's going to behave like a 1 over n. In this case, though, I see an n cubed in the denominator. I see a sine of n, which stays between plus and minus 1. This one has got to be convergent, even if I put absolute value bars around it. So I'm going to go straight for, here's my point. I don't have, if I suspect that it's absolutely convergent, I can go straight for absolute convergence. I don't need to check convergence and then absolute convergence. So if you understand what's happening, you can sometimes bypass that first step and go straight for absolute convergence. So, since absolute value of sine of n over n cubed, right? Now this is a sequence with all positive terms, and that's going to be strictly less than or equal to is all I need, 1 over n cubed, and sum n equals 1 to infinity 1 over n cubed converges. Here, that's a p series where p equals 3. So does sum n equals 1 to infinity, absolute value, sine of n over n cubed by, so what did I use here? I used the comparison test. And so our conclusion then, right? The series where we put absolute value bars around it converges. So the original sine n over n cubed is absolutely convergent. Now, there's a couple of tests that we're going to now use that allow us to conclude convergence, absolute convergence, or divergence, right? So we're actually going to get a couple of tests here. The first one, so let's see, let's put it up here. The first one, and this is one of my favorite tests. So this one's called the ratio test. And it goes like this. So if, and there's 3 parts to this. So maybe I should, how do I want to write this? I guess I'll write it as A, B, and C. So part A, if the limit as n goes to infinity of the absolute value of an plus 1 divided by a sub n, if that limit is strictly less than 1, then sum n equals k to infinity of a sub n is absolutely convergent. Part B of the ratio test, if the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n is strictly greater than 1, then the series diverges. And then there's one last option. What if the limit's equal to 1? And it turns out if the limit's equal to 1, then the limit, or the ratio test is inconclusive. All right, so that means you got to try some other test. So if the limit as n goes to infinity, absolute value a n plus 1 divided by a n is equal to 1, then try another test, right? So then the ratio test is inconclusive. All right, so let's look at some examples. First example, sum n equals 1 to infinity minus 1 to the n, n cubed over 4 to the n, n cubed over 4 to the n. Okay, so I want to use the ratio test here, and the reason it's called the ratio test because you take the limit of this fraction right here, and you just look at the values. So let's look at the limit as n goes to infinity. Okay, so what do? I take the absolute value of the n plus 1th term divided by the nth term. So this is going to be a minus 1 to the n plus 1, n plus 1 cubed over 4 to the n plus 1 divided by minus 1 to the n cubed over 4 to the n. Okay, so now we need to simplify this mess. And so what we're going to do is first notice absolute values just gets rid of all this minus 1 stuff. So we can do away with that. And then I need to flip and multiply. So this is going to be limit as n goes to infinity. N plus 1 cubed over 4 to the n plus 1 times 4 to the n over n cubed. And notice now everything's positive, so I don't need those absolute value bars. That's equal to the limit as n goes to infinity. So let's see, I can cancel some 4's here. And so what I'll get is a n plus 1 cubed over 4 n cubed. And now this is polynomial over polynomial. The degrees match, and so what we'll get for a limit is 1/4, which is strictly less than 1. What does that tell us? It tells us that the original series is absolutely convergent by the ratio test. So, conclusion, the original series it's tempting to abbreviate this RT. Unfortunately, there's also going to be a root test, so I need to write it out. Ratio test and root test. One place where the ratio test absolutely is almost always the thing you use. If you see factorials almost always, you're going to use the ratio test. And so let's see. Let's look at this one. We've actually seen this one before. We used the comparison test to show it converges. The ratio test is actually a little more fun. So remember this one, n factorial over n to the n. Notice all the terms are positive here, so I don't really need to worry about the absolute values. In fact, absolute convergence and convergence mean exactly the same thing because nothing happens when you put absolute value bars around here. Anyways, when I see n factorial, I'm going to use, or anytime when I see factorials, ratio test is what I almost always am going to go to. So when you see factorials, think ratio test. All right, so let's compute the limit as n goes to infinity of n plus 1 factorial over n plus 1 to the n plus 1 divided by n factorial over n to the n. First thing we do is flip and multiply, so this is limit as n goes to infinity. N plus 1 factorial over n plus 1 to the n plus 1 times n to the n over n factorial. Okay, so now let's see, we can cancel some factorials. And that's why the ratio test is useful when dealing with factorials, is because you'll get a fraction with some factorial stuff in the top and the bottom, and those will cancel out nicely. So what we'll get is an n plus 1, and then I'll have an n to the n, and here I have an n plus 1 to the n plus 1. Right? N plus 1 factorial over n factorial leaves me with an n plus 1. Oh, then I can cancel an n plus 1 here, so that's limit as n goes to infinity of n to the n over n plus 1 to the n. And I'd like to combine this all into one piece right here. This is limit as n goes to infinity, n over n plus 1 all raised to the n. And this should look familiar to you. This is an indeterminate form, 1 to the infinity. You can go through the computation if it doesn't look familiar, but it turns out, all right, so you can check that this limit is actually equal to 1 to the e. I'm not going to go through the steps, but you should be able to verify that this limit is 1 over e, which is definitely less than 1. And so what does that tell us? It tells us that this series is absolutely convergent by the ratio test. Let's try one more example. Sum n equals 1, 2. I guess, well, yeah, let's try one more example. Sum n equals 1 to infinity minus 1 to the n over square root of n. Now, when I see this one right here, what I'm going to do the ratio test, but it turns out that's the wrong test to use. But I just want to do it so you can see why it's the wrong test to use. So if I go limit as n goes to infinity, absolute value, minus 1 to n plus 1 over square root of n plus 1 divided by minus 1 to the n over square root of n. And simplify, what we get is the limit as n goes to infinity of absolute value of n over n plus 1. That limit is equal to 1. So what does that tell us then? It tells us, right, the ratio test fails, right? It's conclusive. And that doesn't mean stop. That means try a different test. When you look at that one, you say, you know what? Okay, this one is an alternating series. It's definitely going to converge by the alternating series test. And then if you take absolute values, you get a p series where p equals 1/2. That diverges. So this one is actually conditionally convergent. And what you'd use is alternating series test and then the p test where p equals 1/2. Right? Those two together actually show that it's conditionally convergent. Okay, so as I said, there's one more test. That one's called the root test. And just as the ratio test, it works nicely when things cancel, especially factorials. So the next one, the root test, works nicely when we have expressions raised to the nth power. And we'll see why in just a second. So the root test goes like this. Once again, there's 3 parts. So if the limit as n goes to infinity of the nth root of the absolute value of a sub n is strictly less than 1, then the original series sum n equals k to infinity of a sub n is absolutely convergent. So it's going to look very much like the ratio test, except I'm going to replace the ratio with the nth root. Part B, if limit as n goes to infinity of the nth root absolute value of a sub n is greater than 1, then sum n equals k to infinity a sub n diverges. And then the last example, if limit as n goes to infinity absolute value nth root of absolute value of a sub n is equal to 1, then inconclusive. The root test fails, inconclusive. Try another test. So let's try a couple of examples. First example, sum n equals 2 to infinity minus 1 to the n divided by natural log of n raised to the nth power. When we see some expression raised to the nth power, that's when you want to think root test. So if I do limit as n goes to infinity of the nth root of the absolute value minus 1 to the n over natural log of n raised to the n, that's just going to equal limit as n goes to infinity. Oh, sorry, that should not just be square root, that should be nth root. Make sure I got nth root in all places. Yeah, nth root, nth root, nth root. Limit nth root. Well, I mean, let's see what happens. It cancels off that, so we get just 1 over natural log of n. That's equal to 0, which is less than 1. And so our original series is absolutely convergent by the root test. Okay, let's do one more example. And then you got lots of practice to do with your homework. And this is the last of the test, that root test. So now we know all the tests. So now it's just time to put it all together. So how about this one? Limit as n, nope. We need a series. So sum n equals 0 to infinity, 6 to n plus 1 over 5 to the n plus 1 raised to the n. This one diverges for various reasons. There's various tests that would work on this. Let's do the root test. So since limit as n goes to infinity of the nth root, it's not alternate, these are all positives, so I don't even need to take the absolute value, but the nth root of 6n plus 1 over 5n plus 1 raised to the nth power, that's equal to the limit as n goes to infinity of 6n plus 1 over 5n plus 1. That's polynomial over polynomial where the degrees match. And so this limit is 6/5, right? Which is great, and I should just write it out. This is greater than 1. The series diverges by the root test. Okay, so I think that's a good place to stop, so we will see you next time, okay?